Okay, at the end of last class, we talked about shapes. We were talking about electron geometry, molecular geometry, like the shape of a molecule. And we got to electronegativity, talking about unequal sharing of atoms across a bond. And then finally ended up here at the nonpolar express. So if we look at the Lewis structure for a molecule, just generally, at least in this class, the molecule will be nonpolar if both of these statements are true. Our first point, there's no lone pairs on the central atom. That means we're going to have a molecular geometry of linear, trigonal, planar, or tetrahedral. So no lone pairs on the central atom, and all the atoms bonded have to be the same or have the same electronegativity. If both of these conditions are true, then it will be nonpolar. Now, if we don't have any polar bonds, then it's also going to be nonpolar because we don't have the condition. That's like our starting point, our starting condition. So today we're just going to cover some examples. So starting with CH4 methane gas, the first thing we need to do to determine whether it is polar is we need a Lewis structure. So we're going to have carbon in the middle. We're going to have hydrogens around it. You may remember that hydrogen only forms one bond, so the hydrogens all have to be attached to the carbon. Otherwise, it wouldn't be attached. We've got a carbon. Carbon has 4 valence electrons because it's in our 14 or 4A category, group, column. So it's got 4 valence electrons. We've got 4 hydrogens. Hydrogens each have 1 electron. So 4 times 1 electron each equals another 4 electrons. We've got a total of 8 electrons. And this should be labeled valence electrons, VE. To get everything connected, we need to draw in 4 bonds. 4 bonds times 2 electrons means that we've got 8 bonding electrons. So that's all of our electrons. Pretty simple. And then we can go through and check and make sure that all of our atoms are happy. Each of our hydrogens has 2 electrons. Hydrogen likes to have a duet. It likes to have exactly 1 bond. So our hydrogens are all happy. And our carbon in the middle, carbon has 1, 2, 3, 4 bonds. 1 bond equals 2 electrons. 4 bonds equals 8 electrons. So our carbon has a full octet. So this is a good Lewis structure. Then we need to figure out, is it a polar molecule? So we would check with our yellow sheet or looking somewhere else if we've got the condition for polarity. So for carbon, I don't know what I'm doing with that. Carbon, if I'm remembering correctly, has an electronegativity of 2.5. Hydrogen, 2.1. So our difference in electronegativity is 0.4. That's right on the edge of nonpolar or polar. That's kind of like our cutoff point between nonpolar and polar. So we'll say that it's on the edge of polar. This would probably not be polar. I probably would generally not consider it to be polar, but for the sake of testing our nonpolar express, let's just assume that it does make a polar bond. Okay, so our 2 conditions for the nonpolar express. 1, no lone pairs on the central atom. Do we have any lone pairs on carbon? No lone pairs on carbon. No lone pairs on carbon, which is our central atom. 2, are all the bonds the same? Are all 4 of the bonds equivalent? They sure are. So all bonds are equal. In this case, they're exactly the same. So we've met both of our conditions for the Nonpolar Express. So this is nonpolar. Questions? All right, one for you to try. Determine whether NH3 is polar. So start with that Lewis structure. Make sure that it's a good Lewis structure, and then run through our checklist for that Nonpolar Express and see if it meets both of those points. All right, bringing it back in. We want to determine whether NH3 is polar. So we first would have to come up with the Lewis structure. If you do the Lewis structure for ammonia, you will get this. In order to determine whether it's polar, we have to see if it has a polar bond. Nitrogen is a 3.0 on the electronegativity scale. Electronegativity of 3, and hydrogen has an electronegativity of 2.1, unless I'm crazy, it's entirely possible. So our change in electronegativity, 3.0 minus 2.1, 0.9. That is solidly in the polar region. Watch out, Coca-Cola. Because polar bears like, anyway. So we've got a polar bond, right? Polar bonds. We can go through our Nonpolar Express checklist, our no problem checklist. Step 1, no lone pairs on the central atom. Our central atom here is nitrogen. Do we meet our first condition? Do we have no lone pairs? Or is there a lone pair? There is a lone pair. Nonpolar Express fails, so we do not pass. It is not nonpolar, therefore, since we have a polar bond, it's polar. If we wanted to draw this out in 3 dimensions, which we probably don't, but I'll go ahead and do it anyway. One of the ways that we could do that is like this, with our lone pair on the top. So on the left, this straight line, this hydrogen is in the plane of the board. The other 2 hydrogens, one's coming out and down, the other's coming out and down but to the back. So it's kind of like this, and then the other one's here. And so because we've got that polar bonds, our polar bonds would look something like this. They're all pointing slightly up. It doesn't really represent it entirely here. And so we have an overall net dipole across our molecule. So it'd be the other way that we could come up with it. Because those arrows aren't completely canceling each other out. All the vertical forces, the way that I've drawn it, add up. It's the around forces that would cancel out. So this is polar. Questions about that one? You don't have to know the arrow method, again, because vectors are scary. But if it fails the Nonpolar Express checklist and it has polar bonds, that generally means that it's polar. Okay, determine whether SO2 is polar. Another one for you to try. All right, if you were stuck on the Lewis structure, here is the Lewis structure. That's one of them. The other one would be the mirror image. So those would be the the two Lewis structures. It does have resonance. And our electronegativity values are 2.5 for sulfur and 3.5 for oxygen. I'll give you a little bit more time in case you're stuck on the Lewis structure. See if it is polar. All right, first thing that we want to consider when we're looking for whether a molecule is polar is, do we have a polar bond? Our difference in electronegativity between our sulfur and our oxygen, either of them, is going to be 3.5 minus 2.5, which gives us a value of 1.0, which is definitely polar. Okay, so we have polar bonds. We can proceed to the Nonpolar Express checklist. We have polar bonds. Okay, so Nonpolar Express. First point, no lone pairs on our central atom. Our central atom is the sulfur because it's in the middle. Do we have no lone pairs on the sulfur, or do we have lone pairs on the sulfur? We have lone pairs on the sulfur. Nonpolar Express is a bust, so it is polar. We did not meet both conditions, the other condition being that the bonds are the same. In this case, they would be the same, even though it looks like they're not because we've got the resonance. Remember, it's rapidly switching back and forth between the two, but in reality, it's a hybrid. That was that slide with those cats on it. Any questions about this one? If you want to know how we got that Lewis structure, it did show up earlier in the slide, so you can watch the full explanation there. All right, part of the reason we've been talking about electronegativity and polarity and all this stuff is, remember, oil and water don't mix. Why don't they mix? Well, it turns out it's because of the polarity. So water molecules are polar, they're very strongly polar. Oil molecules are kind of like big versions of this CH4 if you add a bunch of carbons on there. That's basically what a lot of oil molecules are, and so those are nonpolar. Polar molecules and nonpolar molecules do not get along. They don't interact well. So these water molecules can all kind of stack up because we've got the partial positive charges on our hydrogens, we've got the partial negative charge on our oxygens, and so these charges stack up kind of like magnets. Now they don't necessarily like lock into those positions, but they will tend to assemble sort of in that fashion, and they get locked into this position, especially if you got them to like freezing temperature, then they would sort of lock in there. And because of these strong attractions between the positive and the negative, it's sort of like if you threw a bunch of marbles together and they were magnetized, they would all clump up against each other. That's sort of what our water molecules are doing, and when they do that, they squeeze all the oil molecules out. So these all link up, squeeze out the oil molecules, and the oil molecules get pushed out. So this is why, if you've ever gotten grease or fat or something on your hands and you try to rinse it off with water, hot water sort of works, but that's just making the oil runnier, essentially. When you add a little bit of soap, you can wash the grease away, and this is how soap works. So soap has this long tail that looks like an oil. It's got this long nonpolar chain that can interact with oil or nonpolar things. So oils are going to tend to have these long chains, and these long chains can stack up on top of each other, and they sort of interact by something that's sort of like friction. They could also like tangle around each other and interact that way. And so this long part interacts with oil or nonpolar things, and then you have this other end over here. This is what we call a polar head. This part can interact with water. So it's sort of a magnet on a long piece of spaghetti, and the magnet interacts with the water, and so the water molecules link up with that magnet head, and then the long kind of noodle spaghetti arm interacts with the oil. So it kind of allows the water to indirectly, like through the soap, interact with the oil and then pull it off and wash it away. So that's pretty cool. And that's just generally how soaps work. Any questions about anything in the chapter? Great, then that'll do it for chapter 7. We will start chapter 8 on Wednesday.